So now we are ready to talk about the periodic table, the explanation of which was one of the great triumphs of quantum mechanics. We get the periodic table, and I say more or less on the slide, I'll explain why in a minute, by simply filling up the states of the hydrogen atom in order of increasing quantum number. So principally the principal quantum number, and then as appropriate increasing the azimuthal and magnetic quantum numbers. And so this, roughly speaking, gives one the order with which the eigenstates fill up in energy. Now remember that the L and M quantum numbers are degenerate in hydrogen, so look for some surprises when we actually fill up the elements by placing many electrons onto an atom, because it will make some changes. Now, in the periodic table, originally formulated by putting elements in columns corresponding to their chemistry, and then arranged in rows according to molecular weight, the key issue being that each column has elements which have really very similar chemistry. We'll see that the reason for this is that the successive columns correspond to different angular momentum states of the outermost electrons, and it's these angular momentum shapes that determine the shapes, or states that determine the shapes of the orbitals, and hence the chemistry of the atom. We'll show on the next slide how their states are called out, so let's turn to that. So the notation for specifying atomic states is as follows. For example, in the case of hydrogen, it's the 1s state, and it has just one electron in it, so that's shown by a superscript 1. Helium, now we add a proton and an electron, and we fill up the 1s state. Now I've gone on here to the example of silicon, so let's enumerate that. It has a total of 14 electrons, so for silicon the atomic number is 14, and these then occur by filling up the hydrogen atom eigenstates as follows: 2 electrons in the 1s state, 2 electrons in the 2s state, 6 electrons in the 2p state, 2 electrons in the 3s state, and then finally we're left with 2 electrons over, so these go now into the 3p states, which are several states unfilled, and you'll see when we look at the periodic table there are elements to the right of silicon that correspond to filling those states to eventually form a closed 3p orbital. The wrinkle in this ordering of energy comes about with d states. D states penetrate the atomic core considerably, and this means that electron-electron interaction energies are significant. This causes the energy of the 3d states to be elevated up above the energy of the 4s states. So this nice logical hydrogen eigenstate order of filling the states breaks down after the end of the 3p states. We then start with the 4s states, and the 3d states fill in energy after those. Another useful thing to know when looking at the periodic table is Hund's rule. Hund's rule says that in order to minimize electron-electron interactions, when empty states are available, the electrons will go into different m quantum number states, one after the other, but unpaired. So for example, let's take the case of m equal -1, 0, and +1. We would put the 6 electrons into this according to Hund's rule this way. Not necessarily in this particular order, it's arbitrary of course. Now when we want to put the 4th electron, it will then go in as a spin paired set of electrons, and we will continue doing this until we fill the orbitals. So Hund's rule says that electrons go in unpaired when they can to minimize electron-electron interaction energy. So here it is, the wonderful periodic table. So just to remind you about the commonality of chemical properties, down here we have the alkali metals. Hydrogen's a little special, but these are all violently reactive, love to donate electrons. Over here we have the elements with closed shells, so these are essentially completely inert, really don't like to lose or gain electrons because they are in a closed shell configuration. Just to the left of them we have the halogens, fluorine, chlorine, bromine, iodine. These are just one electron short of a full shell, and so love to accept electrons. So we describe these propensities to donate or accept electrons as in terms of the ionization potential. In other words, how much energy does it take to remove an electron? Well, fluorine would really love to have one, and neon would hate to give up its closed shell. So as we go along this way, we decrease the ionization potential because lithium is very happy to give up an electron and become Li+. So going along the periodic table this way, we talk about decreasing ionization potential. The opposite of ionization potential is electron affinity, which is the energy gained by adding an electron to form a negative ion. So chlorine really loves to form a negative ion, for example, because it now has a closed shell configuration like argon, and therefore has considerable energy to be gained by forming a chlorine ion. On the other hand, the last thing that any of the alkali metals want is an extra electron. So already you see an order of chemical reactions as you look across the periodic table. You can see, for example, that lithium would very happily donate an electron to fluorine to form lithium fluoride, and indeed it does. So salts are formed by reactions between elements on the left of the periodic table and elements on the right. As I said before, these elements with closed shells are unreactive. But we can say several other things about the periodic table. Here you see these famous 3D states that should have belonged here had things gone according to the hydrogen eigenstates. In these states we can put 1, 2, 3, 4, 5 unpaired electrons. Now we start pairing them off. So in this region of the periodic table we have unpaired electrons. This corresponds to unpaired spin, and these materials in here are magnets. Hund's rule has another effect, which, for example, is that molecular oxygen, for similar reasons, is a paramagnet. So many of the properties of elements can be understood, even quantitatively, with just this simple idea of filling up states according to their order in the hydrogen atom. So finally, let me just show you some numbers to show just how enormous this effect of forming a stabilized shell, full shell, is. So this is the ionization potential now. First ionization potential, meaning the energy required to remove one electron. It's expressed here as kilojoules per mole. But these are enormous energies. So you see that lithium is relatively easily ionized at 500 kilojoules per mole. Neon at 2000 kilojoules per mole is extremely hard to ionize. All of this additional stabilization energy coming from completing a shell.